Okay, so this is going to be our first lecture for the semester. I've got a couple of weird new things going on. My Surface wasn't working properly, so I'm using this bamboo tablet on the computer. Or on my desktop, I've got a new PDF thing that I'm working with, so bear with me for a little bit as we get going here. Let me go on, and also Camtasia is not working, so that's the other good thing that's happening. I'm having to do this on Zoom. I don't know how well that's going to work though. Okay, so here we have it. This is the first page of lecture notes. As I mentioned in my introduction video, the section numbers are all correspond. They're all meant to correspond to the textbook for the course. So 2.0, there isn't a 2.0, there isn't a 2.0 in the textbook, but there is a section 2.1. This is why we're starting in chapter 2 instead of chapter 1 or something like that. Here are some things that you should know. You should have already known before you started the class. I just want to go over some of them. So if we've got a function of two variables, then this symbol right here, this means the partial derivative of u with respect to x. Another common notation you might see is something like ux like this. Okay, I definitely need to get a smaller pin size here. All right. Or this just means the partial derivative with respect to x. So you might see something like this as well. And I realize I'm writing like a serial killer, but that's because I'm having to do it on the bamboo thing and I'm not quite used to it. Also, the gradient, if I have a function, the gradient is just, again, a function of two variables. This is just the gradient. It's this vector field where the first component is the derivative of the function with respect to u, and the second component is the derivative of the function with respect to y. Or if we're using x and t, it'll be something like that as well. Okay, so now if we have a function, that's a function of two variables, and x is a function of s, and y is a function of s, then the derivative of f, so overall, when we write it like this, it looks like f is a function of two variables, but really x is a function of s and y is a function of s. So therefore, overall, the function is a function of one variable, the s variable. And so we can talk about the derivative of f, just the ordinary derivative of f with respect to s. That's a well-defined thing as long as everything is differentiable. F is a function of s, so we can take its derivative. And this is the multidimensional chain rule. There's a typo here. I'll let you guys think about where the typo is for a moment. It's right here. This x should be an s. Sorry about that. But this is the correct chain rule. This is the chain rule. It's the derivative of x with respect to s times the partial derivative of f with respect to x plus the stuff with y. You might also see this like using different notation that you might also be familiar with. We'll write something like this. And notice we're doing partials for the f. So this is the partial derivative of f with respect to x, but this is just the ordinary derivative of x with respect to s because x is a function of one variable. Whereas f has these intermediate variables, x and y. Okay, and so now we have this other thing. This next thing here is about directional derivatives. Let me go up to a previous page and talk a little bit about directional derivatives. So let me come over here. I'm going to have to, yeah, okay. So let me draw like a generic XY plane here. So this is X, this is the Y-axis, this is the X-axis. And let's say we have some generic point here in the plane. I'm going to call this point AB. And then let's say we have some curve going through this point. This is going off that way, going off that way. We're just going to look locally about the point AB. And let's say that this vector, the tangent vector to the curve at this point is going in that direction. This vector is V, and we're going to call it lambda gamma. Okay, if I have some function, u is a function of these two variables, x and y, then if I think about this point, or if I think about this blue curve, I can think about u as living along this blue curve. If I just restrict u to this blue curve here, it now basically becomes a function of one variable, just going along this one-dimensional curve. And so I can think about its derivative along this curve. And at AB, its derivative along the curve is just its derivative in the direction of the tangent variable lambda gamma. So the directional derivative, we get a different color here. The directional derivative of u, so the directional derivative of u in the direction of lambda gamma. And here we're assuming that lambda gamma is a unit vector, is given by. So here's the notation. This is directional derivative in the direction of lambda gamma of the function u evaluated at the point AB. This is just going to be equal to the gradient of u dotted with the vector lambda gamma. Okay, so this is a directional derivative. It is the derivative of u at the point AB in the direction lambda gamma. And this is going to change depending on whether you pick a different point or a different direction. Okay, this is very important. This is going to be a very important thing to understand this and the chain rule, basically all of these preliminaries, but we're going to use this directional derivative and the chain rule in the next video when we actually start analyzing PDEs and things like that. So you're going to need to understand that. If you don't understand it, look it up, look on Khan Academy or whatever else you need to remind yourself about directional derivatives. Also, watch the next video, and I think when you see how we're going to be using it, it might also help understand a little bit what the directional derivative is. Okay, first order differential equations, in particular separation of variables and integrating factors. So I just want to basically go over the integrating factor thing. So let's say we have a first order differential equation. So it's x prime. I'm going to use this new notation that you might have seen before. Instead of prime, I'm going to use dots to note derivative. So this is the first derivative of x. So we're going to say it's a function of t plus some given function p of t x of t equals some other function q of t. Okay, this is a first order linear differential equation. One way to solve it, kind of the most generic way to solve this, is going to be with the method of integrating factors. To do this, again, you're going to have to look up what integrating factors are. I'm not gonna completely reteach it. I'm just going to remind you the integrating factor is equal to the integrating factor is equal to e to any antiderivative of this p of t dt, and then we're going to multiply both sides of the equation by the integrating factor. And on the left-hand side, when we do that, this sort of magical thing happens. The whole point of the integrating factor, if you'll remember, is that when you multiply the left-hand side by the integrating factor, you just get the derivative of x times mu. And on the right-hand side, just going to be the product q of t times mu of t. And so now if I anti-differentiate both sides, I've got x of t, mu of t on the left-hand side. And on the right-hand side, this is going to be an arbitrary constant. I'm just going to write the arbitrary constant explicitly times the antiderivative of q of t times mu of t dt. And now I can just divide both sides by mu of t to get a formula for x of t. Okay, and we're going to see this in upcoming problems, so I'm not going to do any examples, but again, you need to remember what this is. It's just one of those things that I assume that you know coming into the class. Okay, so that's where I'm going to stop today, or it's not today, that's where I'm going to stop in this video. In the next video, I'm going to show we're going to start actually looking at partial differential equations.